Welcome, everyone, to this oNote training webinar. Our subject today is how to accelerate your development from your event model through your implementation with oNote code generation and Event Store. My name is Bobby Calderwood. I'm the founder of oNote, and I'm joined today with our special guest, Chris Condron, CTO of Event Store. Chris, would you introduce yourself?
How you doing? Chris Condron. I'm with Event Store currently. I started off in dealing with event-driven systems back in the late 90s in telecom as we switched over from switched networks to packet-based networks and voice over IP. From there, I wandered into insurance and finance and large relational databases, and finally came back out when I met Greg Young and started building event-sourced systems, which went from the basic messaging systems to actually building systems where the events were the source of truth and change. And that was very popular in a large number of financial services systems. Since then, I've been building event source systems for nearly the past decade. And recently I've joined Event Store, where I'm helping build out the tools to make it easy and possible in a very good way.
Thank you, Chris. We're so pleased to have you with us. We're really excited about this whole space, event sourcing, building event-driven systems. That's why we built this tool. oNote was exactly to design systems the way that Event Store helps you implement them. So these two tools go together hand in glove. We're really excited to have you with us. So my sort of opening thoughts along those lines are everyone here, certainly those who have signed up for the webinar to join us today are interested in event-driven systems. That's become sort of the norm now, right? We have to be able to respond to our customers in real time, be very responsive to them, right? We have to have a sort of an omni-channel view of what our customer is experiencing, right? We can't deal with them in departments anymore, or have different systems that know different things about our customers. We need to sort of have this unified omni-channel view of our customers, and we need to be able to integrate and build additional sort of digital experiences and integrations with partners and so forth. And we need to do that at scale and at speed. The traditional way of building systems, where you think always in terms of sort of current state, right? Current state-oriented thinking, it's very pervasive. And I think we underestimate the degree to which that style of thinking sort of pervades almost everything we do. So it's hard to make this leap. Everyone wants to make the leap into event-driven. That's again sort of almost table stakes now to be a true digital company. You have to be able to be event-driven and real time, but it's really hard to get over that sort of mental block of the way that I built systems my whole career sort of no longer works. Really, it's difficult to retrain our brains as engineers, think through the way we design our systems with our stakeholders, helping our product folks and so forth to think in terms of event-driven, and then to implement those systems again is difficult. The developer training and developer experience that we have all centers on current state-oriented systems, kind of built around the database schema. So we need tools, and we need ways of thinking or ways of communicating with each other, kind of methodologies for designing event-driven systems the same way that we needed them for current state-oriented systems, right? There's great tooling, there's tons of training, there's lots of developer mindshare and customer and stakeholder familiarity with the sort of current state-oriented view of systems. With Event Store, with oNote, with event modeling, we're starting to develop a great ecosystem around designing, communicating about, implementing these event-driven and especially event-sourced systems. So we're pleased to have everyone join us. To start off here, we think you'll get the most out of this training if you sort of follow the stickies that I think Cash is going to be posting here in the public chat. To start off with, sign up for oNote so you can follow along. We have a repository, which I'll send out here in a few moments, full of these models that we're going to be working on today in oNote. All these event models are available in a GitHub repository so that you can sort of follow along. The code that we'll be implementing later in the training today is also available in this GitHub repository. So we encourage you to sign up for oNote, upgrade your account to Essentials so that you can do the data and schema modeling. Add the Avro PowerUp. We've given or we'll be distributing out a promo code for adding that Avro PowerUp so that you can do the code generation bit where after you've modeled out the schemas, you can actually generate this Avro code. If not, all the generated Avro is in the repository as well. The models are in the repository. So at a bare minimum, please do clone this GitHub repository that I'm about to send out in the public chat. And there we go. So do clone that GitHub repository, and you can follow along in the pizza delivery. Oh, that just disappeared. There we go. There, I just sent it out. You can follow along at home with this training as we proceed. So, as I sort of outlined at the beginning, why do we need event modeling? Why do we need oNote? As I mentioned, my name is Bobby Calderwood. I started this company, had a reason to do so. I've been building event-driven systems for a long time, most recently about 4 years ago at Capital One, building big event-driven event streaming systems in the finance domain, banking domain, and saw the real need for a way of thinking about these event-driven systems. Again, there's a sort of this gap in the developer understanding and in the tooling around how to design and implement these systems, and stumbled across a great methodology called event modeling. Event modeling, we didn't create that. Event modeling is created by a friend and colleague, Adam Dimitruk. He's the CEO of AdaptTech Group. And he invented this way of thinking about event-driven systems that distilled kind of the best parts of domain-driven design and borrowed some concepts from like event storming and some other related modeling disciplines, and sort of distilled it down to this very simple modeling language. It only has 4 elements in this whole modeling language. It's very easy. It's visual, so you can engage your stakeholders and they can see and visualize what's going on. So it's a visual language for describing and defining event-driven systems. We used event modeling, loved it, and at the beginning we were sort of doing it with sticky notes on the whiteboard or on the piece of butcher paper on the conference room wall, and that was great. During design time and during kind of the workshop time, we learned a lot. We shared a lot of context with our business stakeholders and our subject matter experts, and that was fine. But at the end of the artifact, at the end of the workshop, the artifact we were left with was this big piece of butcher paper covered in sticky notes, right? It's the artifact left a little to be desired. So, we had people taking panoramic mobile shots, mobile pictures to try to capture and digitize this artifact. We saw the need for something a little more enduring. So we built oNote to accelerate the event modeling process during design time. But then once we've built this model, what we've got is this great data structure that represents the system that you want to build. So then from there, we have begun to implement code generation, some project management functionality, some real-time collaboration, repository-based sort of asynchronous collaboration. There's a lot of features that we're working on now and that we have in the product to take event modeling out of just the domain or just the design part of the software development lifecycle and into the implementation and even throughout operations. This same artifact, this event model, is a blueprint for your system, while you're designing the building, while you're constructing the building, and also while you're maintaining and repairing and operating this building. This same artifact is extremely useful throughout the software development lifecycle.
It's a blueprint for what you're building. It's a measure drawing of the application.
Exactly. And it focuses on the right things. And so I'm going to take you through sort of the event modeling workshop process, what that sort of looks like. Obviously, this is condensed. We only have a couple of hours here, and we've got a lot to cover. So a typical event modeling workshop would take, anywhere from 2 to 4 to sometimes even 6 hours, depending on the size of your domain and the size of your team and so forth. The domain that we're going to be modeling today is very simple, extremely simple. We've deliberately kept it that way so that we could focus in on the good parts. And the domain is basically this. So we've all ordered pizza in the last 10 years, hopefully. Pizza's delicious. A lot of pizza delivery apps, you place the order on your mobile phone or on your web browser or whatever. Or sometimes even you can call in and talk to a teenager and ask them to make you some pizza. And then after your order's placed, you get this really cool tracker, like this pizza tracker thing where you can see where your pizza is in the process, right? It's someone's working on prepping it. Okay, now it's in the oven. Okay, now it's prepping for delivery. Now it's being delivered. Now it's at my door. Okay, great. So you can sort of visualize as the customer. You can visualize kind of what's going on with your order, and then if there's a problem, you can call the store or whatever and take action. On the flip side of that, you've got sort of the fulfillment team who's responsible for sort of building out and delivering your pizza. So they need to see what orders are placed. They need to sort of claim those orders and prepare them, put them in the oven and sequence the delivery of these pizzas. And then when they're delivered, they need to confirm that order was delivered so that they can move on with their life and take your money and all that stuff. So there's kind of the domain that we're modeling right now is not the order taking part. Like we're not talking about shopping carts and pizza toppings. We're talking about after the order's placed, how does the fulfillment team sort of track their own work through the process? And how does the customer visualize where their specific order is in the process? So that's the domain that we're going to be modeling today. Very simple, but very customer impactful, right? We probably already have an order taking system somewhere, provided that system can expose the important event of when an order was placed. We can not even worry about the order taking system and just downstream of that say, okay, the order was placed and now we've got everything we need to know to build out this domain, provide a very valuable digital experience to our customer, streamline the operations within our store. So that's the domain that we'll be modeling here. What you see on the screen is oNote. This is our event modeling tool. What you're seeing here is the very first step in an event modeling process. So an event modeling process starts with just sort of brainstorming all the stuff that happens during the domain under consideration. So what happens, right? Well, okay, we know that the order's placed. That's sort of our starting point. So we know that that's something important that we need to keep track of. Great. What else is going to happen? At some point at the end here, the order is delivered. Great. So in oNote, it works very much like a spreadsheet. You can kind of move your cursor around, and anywhere that the cursor is, you hit enter. You can begin typing, hit enter again, and that saves the model element that's appropriate for that position on the screen. Down here at the bottom of the screen, we have these lanes or these streams of events. So we have a stream of events about orders, and then we have a stream of events about the fulfillment of those orders. And these are sort of independent stories. These are things that happen, and if you just follow one stream, you should be able to sort of reconstruct what's going on in your business. But down here at the bottom, everything sort of south of this gray strip across the middle, which is called the timeline, everything below that is all about events. This is about just the facts. These are the things that happen that are notable and impact the state of your world so that you need to write them down. So we're going to write down and kind of capture all these different events during this brainstorming kind of period of the modeling session. So we can hit enter in oNote. We can type some stuff, order, paid. And then if we hit tab, we can actually continue to enter. So again, very much like a spreadsheet, we can brainstorm very quickly. Great. So this is our brainstorming process. You can hit escape or enter to exit the editing mode. So this is sort of what you'd see in your first step in your event modeling journey is you just try to get on the board kind of everything that happens. There are no wrong answers at this point. You can list anything and everything that may be happening. in this business process, inevitably you're going to go out of scope. Right here I have an order paid event. Yeah, we're not tracking about when the order's paid. That's somebody else's responsibility, right? What we're talking about is the fulfillment of these orders. So we'll probably end up deleting this order paid event and some of these nonsense events here. Order delivered is, maybe just a special case of the order status being changed, right? We change the order status to delivered. So we can condense, generally you'll go expansive first. It'll be kind of a diamond shaped modeling process where you'll go really big and then you'll tighten it back down. But in this first step, don't worry about tightening it down. Get everything up on the board, all the garbage nonsense events, totally fine. And then you can move on to kind of the second step. So this is just the brainstorming step. The second step of your modeling process is what we call the storyboard, where you try to sequence these events along the bottom. We're really sort of collapsing Adam's steps 2 and 3 here. We sequence the events along the bottom and make sure that they're in proper sort of causal order. They're not necessarily chronological because these events may recur and so forth, but we have them in sort of rough causal order along the bottom here. And then along the top, we sort of have them lined up with what the user is experiencing at that part of the journey. So again, this is very much like a storyboard in film. You start with the script when you're writing a film. You start with the script, and that's sort of the events along the bottom here. That's our event brainstorm and then our event sequencing. Once we have sort of the rough plot points in the script, we can start to think about the visuals. What are we going to show the user when these things are happening along the bottom? So the events represent your script. These are the things that happen, the plot points. The interfaces, everything north of this timeline along the middle here, everything north of this timeline is all about what the user is touching and seeing and experiencing at that point. Often these interfaces are graphical. So here we have 2 Figma interfaces where you can actually import and manifest what your UI UX designers have built in Figma. So you get these really pretty pixel perfect UIs here. Our designer Joe made these. They're excellent. I did not design these, and you can tell when we get to the point where we're implementing the UI. The UI is super ugly. It doesn't look anything like this, sadly. But yeah, so we can model these things in Figma, so we understand kind of what are we really trying to build in terms of these events, or in terms of these wireframes. And here we know that we have 2 audiences. So whereas down here at the bottom, events are organized into streams or kind of stories, right? These are what we call bounded contexts or domains. These are causally independent narratives of things that happen. We'll talk a lot more about that, especially when Chris describes sort of data modeling in events source systems. Up here, the lanes have a slightly different meaning. So when you're in interface land, you're thinking about who is experiencing this. So this is about audience. Down here at the bottom with the events, we're thinking in terms of what story do these belong to? Which plot line in the script do these events belong to? Here at the top, we're talking about who's in the shot, right? We're talking about the characters that are on screen at this point in our movie, right? So we've got this sort of storyboarding process. We can see, okay, roughly at the time that the order's being placed, or maybe shortly thereafter. So maybe we can sequence this over left a little bit. Shortly after the order's placed, someone on the fulfillment team is going to see that order show up in their order in process UI, the thing that shows them what they need to make and who they need to deliver it to and all that stuff. So then we sort of slide to the right a little bit here, and then we have another character in our movie, the customer. And the customer is going to be seeing this sort of pizza tracker thing. Hey, thanks for your order. We've got this like status tracker kind of progress indicator thingy here, and that's what's going to show us, where the pizza is in the pipeline. So the customer is seeing this, whenever the order status changes. So maybe we move this kind of 1 to the left here. Whenever the order status changes, that's going to be reflected in the customer's view. All right. So that's kind of steps 1, 2, and 3 of Adam's workshop format. If you've read some of Adam's writings on event modeling, especially his kind of defining blog post about what event modeling is. He talks about sort of the 7-step process. We're already through the first 3 steps of that process here, kind of building this out. That's what we call the storyboard, where it's events along the bottom and wireframes or interfaces. We use the terms wireframe and interface sort of roughly interchangeably. Interfaces along the top, events along the bottom. That's our storyboard. That's the conclusion of our step here. It is worth noting that there are different types of interfaces here. So if I wanted to add an interface up here, we can just type it like anywhere else and hit enter. That adds sort of a blank interface. If you're just kind of brainstorming and you don't want to think about pixels and buttons and stuff, you can just throw up basically a sticky note of an interface here just to have kind of a placeholder. If you right click and go to details, or if you hit shift enter, you'll be taken to this details pane. And you can do this with any of the model elements. We'll dig into this quite a bit more later in the training. But you can sort of dig into any model element by viewing its details. And in this case, we have an interface designer where we can go and say, okay, what type of interface is this? Okay, this is currently it's a blank interface, it's just a placeholder. But we can actually design a REST interface where we're talking about, get at some resource. And then what we're showing actually represents not a graphical interface, but a web service interface. This is something you might expose to customers or to third-party developers, or if you're building a developer ecosystem, maybe the tool that they're using isn't graphical all the time. Maybe sometimes it's an API where you're exposing some capability via API. That's still an interface, and we still want to show it as an interface. So we have this REST type interface. We can also change this to a Figma, as I've shown you. Yep, from the change. We can show Figma, which is just a Figma embed URL. You just paste in the URL to your Figma document. We also have a job type interface, which is worth mentioning here. A job type interface comes in when we're doing some systems integration, where we're processing, we're listening to somebody else's events come in, and then we're processing those and doing something with them. Or maybe we've built up a to-do list of work that we need to do, like talk to our payment processor. We can build up that work, and then this little automated job here. It's not something that any customers will see necessarily, but it's out there. It's reading from our read models, and it's issuing commands, which we'll talk about in a moment. So it's worth mentioning that we do have a automation or a job type interface as well. Proceeding to step 3, we have now we're trying to empower our users to introduce change into the system. So before, we just had made note of the things that happened. We didn't say how they were caused or what caused them to happen. We just said, okay, here's the things that happen. These are the orange sticky notes at the bottom. Incidentally, oNote is named for those orange sticky notes, oNote. We had those events at the bottom, but they didn't really have a cause. They were just sort of there. Most of the time, our events in the system are going to be caused by our users doing something. And that's how we empower our users to make those changes or to introduce those changes, is by way of a command. So we've got 3 of our model elements here represented on the screen. We have a interface here, which is what the user kind of touches and feels in order to interact with the system. The way that they introduce change into the system is they send from the interface that they're touching, they send a command. And the command is a speculative, untrusted request for action. So this is our customer telling us, do something for us, please. Or in this case, our fulfillment team saying, I need to change the state of this order. Please change the state of this order. But this also represents sort of a transactional moment for us. We can get this command. We can receive this command from our user, and we can say like, no, right? We can say, you're not logged in. We don't know who you are. You're not one of our employees. Why are you using the fulfillment app? Or, hey, sorry, this order's already been delivered, so you can't change its status anymore. Once the order's been delivered, we can't put it back in the oven, right? So we got to think through our domain a little bit here. And this command represents that transactional moment where we have the opportunity to do that. We have the opportunity to say, is this a valid thing that they're asking us to do? If so, great. Then we can emit an event. Once we write down the event, that thing's a fact. Everyone's got to deal with the fact that this has happened, because once we write it down as an event, it is true. If that turns out to be an error down the line, then we'll have to write a corresponding sort of event to compensate for that error. But there's no deleting things. There's no going back. You can't rewrite history. You have to just kind of deal with it and then proceed forward. Okay. So commands are how we allow the user to introduce change into the system. And in this case, the customer at this point can't really do anything. They've already done their bit. They've submitted the order, and that's all the state change that the customer can do during the fulfillment process, right? They're not going to get their hands dirty and put the pizzas in the oven themselves. They're going to wait at home on their couch for the pizza to show up on their door. So they're out of the action business. They're not issuing any more commands. At this point, the burden is on the fulfillment team. So they're the ones that are going to be changing the state of the system, and the way that they introduce those changes is by way of commands. The next step in our journey here is to inform our users. Before we can expect our users to take, reasonable actions, well-informed actions, we need to inform them about what's going on in our system. And that's where read models come in. These green sticky notes are called read models. And these represent materialized view of our state. This is probably the part of our system that we're most familiar with from current state-oriented system design. Everything in current state-oriented system design is just a read model, right? We're just sort of maintaining the current state of everything, and that's what we read, and then we write against that. In this world, we're applying a discipline known as CQRS, Command Query Responsibility Segregation, which simply means we think about the writes and the reads in our system independently. We don't, combine or conflate or complex those things together. We separate those things. That starts during design. That's why we have two different colors of sticky notes for reads, which are read models, and writes, which are commands, where we're introducing change into the system. So we have commands and queries segregated in our design, and then we'll see that reflected in our implementation. When we go to implement stuff, we take completely different paths. It's not like we're just banging on some mutable object or something. We're writing events as a result of our commands, and then we are incorporating those events into our read models to then show out to our users. So everything's sort of mitigated and linearized in terms of causal history by these events, right? We're not just reading and writing on some mutable thing. We're emitting immutable events, and then we're building views of state necessary to inform our users. So here, of course, we need to have some sort of database someplace that shows us what orders need to be fulfilled, right? This is our to-do list. This is the set of the work queue or whatever, basically for this store. Here's all the orders that have come in that we haven't delivered yet. Okay, this represents something important to us, and so we gather that up into a read model. This is a business valuable thing because this shows us the work that we have committed to do for our customers and the work that we're responsible to perform and fulfill. So we're going to gather up, it starts with this order placed event. That's the first thing that kind of notifies us that, hey, there's a new order that we've got to fulfill. And then, so that's the first kind of input into this read model. The first event that we aggregate into this read model is this order placed event. Then downstream, we actually place the exact same read model. So we don't recreate this. We actually copy and then paste the read model in a subsequent place. So it's the same read model. It'll have the same schema when we come time to talk about that. The definition of the read model is the same. It's just placed additional times along the timeline. This is a very common pattern. There are many different events which will cause an update to a read model. And so we need to represent, arrows never go backwards in event modeling. Everything just proceeds from left to right along this timeline. And so we'll obviously need to place a given read model multiple times. Sometimes we'll place a given event or a given command or a given interface multiple times, but it happens most often with our read models. So here we have a read model occurring twice, because the first thing to affect the state of this read model is the arrival of this order placed event that comes from upstream of us. We don't know how that's caused. We just observe it. And then later, when we emit this order status changed event, that order status change will also affect this orders to fulfill. As the order status changes, obviously we're going to change the status of the order that we have aggregated here. And then when the order status changed to delivered, we're actually going to remove that order out of this orders to fulfill read model because it's been delivered, right? So it's no longer a pending order; it's a delivered order, and we can pull it out of the queue of current work. So that's how we model and think about this system. And at this point, we've got a pretty complete picture of the data flow and the experience of our users and the data flow in our backend system. The timeline represents sort of our communication protocol between what the users are doing with the interfaces that we distribute to them, and then what goes on behind our firewall where we're writing stuff down and keeping track of stuff. The stuff we write down and keep close hold on are these events back here. The wild, wild west is up in the interfaces, right? That's where, that's public internet and anyone can do anything all the time. So we have defined along this timeline this vocabulary of commands and read models, which represent sort of the communication protocol, or you can even say the web services interface definition for our system. That was a lot of words for me in a very short period of time. Let's go ahead and take questions. Are there any questions? Go ahead and drop them in the Q&A tab. The chat we can use to coordinate. There's a Q&A tab in the BigMarker interface. If you just click that Q&A, ask questions. We'll try to get them answered. We can do that kind of asynchronously throughout the event. My team from oNote, Mike, Joe, and Cash will be online. They can answer some questions as well. But if you have a question and we're, blown through material at the time, just go ahead and post it here in the Q&A. Looks like there are no questions at this time, so we'll proceed with the workshop. We've gotten to step 4, and we have a pretty complete picture of the data flow. If you notice, we have this sort of this set of arrows. Oh, we didn't talk about the arrows. So here in our step 3, we're moving back a little bit. If you see when you hover over any of the nodes in our interface here, you get this little line or this little arrow. This is sort of a drag handle or a connection handle or connection port. So if you drag from this arrow, you'll start drawing a line. And then if you hover over a node that is a valid connection that you can make, the arrow will turn green. If you're off, not on a particular node, it's yellow. And then if you try to connect it to something invalid, that's it'll draw a red line, and it obviously won't be able to make that connection. Causal change always flows from interfaces to commands, to events, to read models, and then back up to interfaces. So we can draw these arrows, pretty straightforward to do. And then if we go back to step 4, the net result is that we have this really nice sinusoidal information flow. So we have this almost like a sine curve here where we start with an event that gets incorporated into a read model. We display that read model on an interface to inform our users about what's going on so that they can make good decisions. Once the user makes a decision and wants to change the state of the system, they issue us a command, which we then record as an event. So they send a command to us, and that's our moment to say, like, I don't know if we should commit to this. Once we've decided to commit to it, we write down an event, and that captures the user's intention and the decision that we chose to make at that point. Those things are captured and recorded in an event. And then that event is subsequently incorporated back into a read model, and the whole cycle starts over again. So we've got this really nice sine wave of information flow. This is great for understanding our systems, understanding where the data comes from in our systems. You get a very good sense for sort of data provenance here. InfoSec and application security people love this stuff because they can see exactly where did a particular data element originate. Oh, well, it started on this screen, and it was sent via this command, and then it ended up in this event, and that's how it got into our world, right? So we can really see and track the origin of all the data in our system. Once you've gotten your model to this point, you're in pretty good shape. There's additional steps in Adam's 7 steps that he talks about for defining these lanes and sort of organizing things, the way that your organization works and the way that you're sort of thinking about your causal narratives down here in the event streams. And then up here, enumerating and elaborating different audiences. Maybe there's another audience in here, a manager who's just responsible for sort of keeping track of any orders that may be slow to be fulfilled or whatever. So there's probably other audiences that we can interrogate and tease out here. For the purposes of this modeling session, we won't do that, but there's additional steps in Adam's 7-step methodology for teasing out all those additional cases. Who else do we need to be informing? Who else do we need to be rolling up stuff about this for the accounting team? As we fulfill orders, should we update our inventory? We're drawing down on pizza dough and sauce and cheese. Should we be drawing down a corresponding amount so we can better manage our supply chain? There's all kinds of different things we can do here when we break down and simplify and envision our state this way. We can integrate and extend these systems to our heart's content. Anything up to this point, Chris? Anything that you want to add, or did I miss anything?
I think that you've really nailed the timeline and how to separate out what we're doing from place to place. One of the things I'd also like to talk about here is, when you're building a system, you have to sort of build it in your mind first to know what you're going to code and what you're going to build. Yep. And this timeline, the first thing you can do is you just sketch out, like, what do we need the app to do? And then you get this rigor around what events do we need, and then what data points are going to go from item to item. And very often I find you backtrack, you find like, oh, we need to do this here. We didn't realize that meant we needed an event here. And so there's lots of different things this pulls out. So you wind up with far fewer misses in the data model and the behaviors. Yep. Because you're providing that rigor to say, I need to know how my information flows from event to read model to event to action. If I've got to know my customer's age in order to know whether or not I can process their credit card, did I collect it?
Yep.
Right. And then if it's personal information, did I store it? Right. So, if the age isn't there, I can't do a command that has a constraint on how old you are.
Yep. Yeah, exactly. And the that sort of gets to when you break your systems down and think about them this way. First, you have to design and build the system in your head. But in almost all, at least enterprise contexts, you also need to communicate that system to other stakeholders, right? You've got business stakeholders who care about how this thing turns out and have metrics that they're measuring and they care about. You've potentially got auditors and compliance and legal folks who, in that example you just cited, did we know this person's age before we, underwrote a loan for them? Did we know their zip code or their race? If so, that's bad, and we have to make sure that we don't know those things or incorporate those elements into our loan underwriting decision, because that's against the law. We don't want to be discriminatory on the basis of race or geography. So there's a lot of those sorts of cross-cutting concerns that when we get into sort of current state myopia, it's very difficult to envision those downstream use cases and plan for them. Yeah. In this case, we don't even necessarily need to plan for them. As long as we're doing our work properly and kind of recording and showing our work, it becomes very easy to build additional read models, additional views of state that slice things in a different way.
That you'd never considered when you wrote the first system.
Exactly.
You've got the events are the business objects. You can build a new business application on top of this that you didn't consider in the beginning, and all the data is there. Yes. And it comes up fully ready to run.
Yep.
The other thing is I find the business people you work with find this methodology very, very natural.
Yes.
You get them to say, well, how would you do this if you just had paper? Or you were just going to send emails between people.
Yep.
Right. And they'll say, oh, well, I would do this, and I would tell him I'd ask this guy for this, and then we need to know this. And those just become your events and your commands and your flow.
Exactly.
I need to ask Bob if we can do this. That's a command.
Yep.
Right?
Yep.
Well, once the pizza comes out of the oven, I can't put it back in. That's a constraint and an event.
Yes.
Right?
Yes. And I love this particular domain for that reason, because for many centuries before computers came on the scene, restaurants had solved this, right? We already had this figured out. We had little pieces of paper, and for each order that the cashier, or whoever was taking the orders, maybe the waiter, for each order that was taken, they wrote down an order ticket, and they put that order ticket up in the, the rotating thingy. I don't know even what it's called, the rotating thing. And the chefs behind the scenes are just, rotating this Turing machine and taking off these pieces of paper, making food out of them. And then they put the receipt with the dish, and then the waiter takes that out to the plate. Right. So they had this figured out long before computers came on the scene. And that's precisely the way in which we're modeling this using commands, events, and read models.
And that model also has a number of additional benefits. So one, you've got a ticket with the entire order for the customer on it.
Yeah.
You've got a ticket that goes into the cook and comes out. So they've got a nice processing.
Yep.
But it also allows you to audit and know whether or not anyone is cheating or skimming.
Yep.
Because
you stick one copy of the receipt on the pin, right? On the pin, you stick that. Next to the cash.
But the thing is, the order book, every order is numbered.
Yep.
So they don't talk about this, but there's a number at the top, and at the end of the night, they count them all out and they see if there's any missing.
Yep.
Because if you have an order ticket that went out and got cooked but didn't show up in the cash register, that means somebody else got paid for that meal and not the restaurant. So that sequential ordering in the order book is actually a sort of a hidden feature in there.
Yep, absolutely. So as we talked about, the other kind of big benefit for this is being able to track the data as it flows through your system. With just this pictorial view, you don't necessarily get that. You don't get the sort of the data elements as they flow through the system. So oNote has a schema modeling system for defining out, what is the shape of the data that we're talking about here? When we store or perceive this order placed event, what are we talking about? Well, is this a map with some keys in it? Is that some binary blob? Like, what is this thing? Because it has a schema, right? Even that little order book has a schema. It's got line items and quantities and the whole thing. So there's schema to these data as we capture them. So it's important to model that in your domain. So here in oNote, if you upgrade to Essential, I noticed that some people are having a problem adding payments. That may be a thing with Stripe. So we'll get that worked out. If you're interested in signing up for oNote, please reach out to Cash and he'll help you get upgraded to Essential. Once you have Essential, you can do this schema modeling. So here we've sort of pre-populated some schemas where we say, what is an order? Do we have a data structure for it? In what status in what states can these orders be? So here is probably a very simple one to start with. We just have an order status enum. There's 5 states that an order can be in. It's either actually, we can add another one here. That this isn't a good schema because there's also an initial state which is placed, right? So we can do our modeling here and say, okay, all orders start placed, and then someone picks them up and is working on them, stretching the dough and adding the sauce and cheese. They slide it in the oven, or the pizza pull guy, puts that in the oven, pulls it out, and then it's en route to being delivered. That includes maybe expediting and getting into the car, on being in the car, and then once the driver scans the barcode on the outside of the pizza box, that thing is delivered. So these are the states in which an order can be in, and this is where you can have a really productive dialogue with your business stakeholders, right? They already have answers to all these questions. We don't need to invent this stuff, right? Software engineers. Let's just ask them, like, okay, what states can this thing be in? Great. What are the different types of orders we can get? Okay, right now we just have 2 types, delivery and carryout. Easy peasy. We handle carryout orders and we fulfill those differently from the way that we fulfill delivery orders. So we need to sort of take that into account in our model. Now, what does an order look like? Let's have a look at this. Okay, so we've defined a map schema. And here's sort of the sequence of keys that we have in our map. Order's got an ID, which is great. You want that sort of traceability that Chris was just describing. And then an order is primarily a set of line items, right? It's a set of things that the customer wants from us. I want a cheese pizza. I have three large cheese pizzas with extra pepperoni, whatever. I guess you can't have a cheese pizza with pepperoni. Anyway, so you have an item ID that represents sort of whatever it is in your product catalog or your menu. You've got a quantity, right? How many of them does the person want? What's the price that you're going to charge this particular user for that? Maybe there's a list price that they're seeing that's different from another price or whatever. So we got to capture the price here. We want to capture any notes, maybe some extra sauce, easy cheese, extra well done bake or whatever. And then, we're going to capture the subtotal, tax, total, just some sort of accounting details here. We're going to store them as integers because we're not going to store them as floats. We're going to store them as integers of cents. Please, data modelers, please don't store prices as floats. And then, maybe we have a logged in customer sometimes. This could be an optional key maybe, but this customer might be logged into the app. And so we actually know who this is. And so we can start associating their order history with that customer. We can build new read models or even machine learning and predictive analytics based on, the history of our interactions with this particular customer. That's another huge benefit of designing systems this way, thinking about the narrative of events first, is machine learning and analytics is like a dead easy afterthought, right? There's no more extract, transform, load, and try to guess what was in the application developer's head to try to recreate stuff like that. We're out of the business of that. We're writing down everything that we're doing. And so it's very easy for downstream folks. Downstream folks like analytics are now first-class citizens. They get this access to the same data that the transaction processing developers are using to build their own read models, right? I'm building my transaction processing concern read model. Sometimes we call that an aggregate. But then there's also downstream materialized views for all kinds of different purposes, but we're all singing from the same sheet of music. We're all building those views of state based on the same narrative of business events. So we've got a delivery address, especially for a delivery type order, we're going to need to know where to bring that thing. And then we've got a type and a status. And these are actually references to those schemas that I showed you earlier. So we can define these schemas at the top level. So if you go to the left-hand side of the oNote tool, there's a button that says Manage Schemas, and that shows you kind of all the schemas that we've defined in our event model. That's great, especially for reusable stuff that you're going to reuse kind of throughout your model. It's good to define at the top level. However, what really becomes powerful is when we start associating these schemas with particular model elements. So here with our event, we're going to drill into the details here, and we're going to go to the Schema tab. And the Schema tab shows us, okay, what schema is associated with this event? When we store this event, what does it look like? Okay, well, in this case, it's just an order. When the order is placed, it's just the order. That's all we care about. We can define a new schema that has a different role. And when we define this schema, we can select an existing schema if we want, or we can define a new one. When we define this schema, it will also be saved at the top level. So we'll be able to reference it from that other kind of all schemas view. But this is very valuable because we can start to drill in and start to see, what is a given event model or a model element look like. So a particular event, looks like this. It's this this order schema. That's what shows up on our front door when we observe this order placed event from whatever upstream system generated this event. This is what we're seeing. This is the data that's available to us to incorporate into this read model. Events are pretty straightforward. There's really just one schema associated with an event. That's the default role that schema plays in that model element. With commands and read models, it's one step more complex, because commands and read models aren't just data at rest. They represent a conversation, right? They represent sort of an exchange of ideas, right? So the interface asks us a question. That's the request. In the case of a read model, we have a request schema. So let's say, okay, Avro request. We can do an existing schema, or we can say, okay, let's define com example pizza. And we can say that this is a orders to fulfill request. And this is the question that the interface is asking of the system. Sometimes you don't want to see all the orders that are available. Maybe you want to paginate them, or maybe you want to just see one particular order, or you want to filter them on some criteria, or whatever. That's what you would put in the request for a read model, is the query. That's the question that you're asking. We can just, in this case, let's just call this a map. It's going to be a map with no keys at this point. In this case, we don't care about the question so much, but we do care about the answer. So after we've asked the question of this read model, hey, show me all the orders, for this customer. Show me all the orders that are in this status, or whatever. Now we can define the response. What is the answer that we're going to provide to this interface? Whoever's asking us this question, they're going to ask us a question, and we're going to send back a response. So the commands and read models are a conversation. So you have to have a request and response schema defined for them. So we can say, we already have something for that, I think. Yeah, we just have an order. Or we can define a new one that's maybe a example pizza. And maybe, I have this backwards. We'll call this orders to fulfill response. Example pizza. And then we can define, maybe this is actually a map with a particular key. Maybe we've got an orders key. So in addition to just the order data that we're getting back, there may be pagination data or other things that we want to send back. So we're going to nest the actual orders that we're sending back inside of this object so that we can add additional, like I said, pagination or whatever to it. So the key is named orders. The type of that thing is we're just going to make it a sequence. It's just an array basically, and it's going to be an array of reference to an existing schema. So we've already got an order schema. So let's just make it an array of orders. So we can do this data modeling, and then it builds us the simple map. The map only has one key, and the value of that key is a sequence of orders. Okay. So once we've defined kind of command and request and response schemas for our read models, we can do the same for our commands. We can come here. Let's actually go to step 6. We can come here to our command, and we say, all right, we've got a request and a response schema defined for this command. In this case, the request is actually the command. This is the interface telling us, do this for me, please. That's an HTTP post or a put or a delete, some unsafe request that the interface is telling us, do this thing for me, please. And so the request is where all the interesting stuff is from a command perspective. So in this case, we have this Avro request schema that we've defined, and we're just trying to set the status of an order, right? Mark order request or change order status or something. Probably change order status is a better name than this. But in that command, we just have an order ID, right? It's just the order that we're talking about. And then we have the status that we want to set that order to be in, right? So it's a very simple command. We're just saying, hey, for order number 1, 2, 3, 4, I'm letting you know that it's in the oven. Great. Very straightforward state change. And then we do need to respond to that. So when the customer or when the fulfillment team tells us, hey, I just put order number 1, 2, 3, 4 in the oven, we need to tell them something. It can be as simple as like, great, thumbs up, yes, good. Or, maybe there's an error that we respond to them. Or maybe we say, no, you can't change the status of that order because Bill already put that order in the oven, and now we've got, a problem. We've got two orders in process, by different people or whatever. So there's, invariants that we can assert here at the command handling time. But ultimately, we need to send a response back to the interface saying, yep, we heard what you said. Great. Sometimes we can even reply with the updated state. That's kind of what we're used to from current state-oriented systems with Event StoreDB, which we'll get into here in a moment. It's very straightforward to respond to that command with, oh, great, we heard what you're saying. Here's the new state of the world for a particular projection or read model. Here's some information about where that event slotted in the log so that we can coordinate our distributed system. There's a ton of really great stuff that we can do in Event StoreDB to respond to these commands. So to review, with a read model, you need to define a request and response. And the request and the response in the read model are, the request is the query, that's the question that the user is asking, and the response is the actual read model. That's the data that we're informing our user with. Commands, it's the opposite. The request is the command itself. That's what the user is telling us to do. And then the response is some indication of what we did about that. Yep, we wrote it down. We heard you. Got it. 202 accepted. Or maybe it's 201 created, and we respond with the current state or with the hypermedia to allow them to view the current state or the state as of the time that event was put into the log or whatever. So there's a lot that we can do. But the point is, for commands and read models, it's a conversation. So you need a request and a reply. With events, we're just talking about what gets stored. So it's just data at rest. We can just define the default schema, and that suffices for events. Again, that was a lot. Questions, please. Love to hear questions from the audience. We've had a grand total of 1 question. When you copy and paste a view, if you update one, will it update the other? Yes. Yep. So there's one shared definition. So we've broken out all the model elements into the definition of the command, read model, interface, event, whatever, and its placement on the canvas. So what you're looking at are actually placements, but behind those placements, like when I pop open the details view, behind the placements, we have the schema. So if that model shows up somewhere else, it'll have the same schema, it'll have the same description, it'll have the same name, etc. Because we only define these model elements once, and then we just place them multiple times along the timeline. Good. So then, if we plug into our final model here, We've defined schemas for everything. We've got all the schemas in place for our commands, events, and read models. And now we're ready to go. So again, we built oNote not just as a design time tool, because we found in our experience that if you just have a whiteboard, a collaborative whiteboard, or a drawing tool like Visio or something like that, you draw all these pretty pictures during design, and then when it comes time to implement the system, those pictures drifts rather rapidly from the reality on the ground. Unless that, yeah. Have you felt that before, Chris?
I oftentimes when I do event storming, I'm like, we're going to spend half a day, we're going to put it up on the wall, and when we're done, we're going to leave it there. And the real value is our shared understanding.
That's right.
And not what we put on the wall.
That's right. That's been my experience with most modeling disciplines, event storming included in that. I do like event storming, but the artifact, again, leaves a lot to be desired. Event modeling is this great sort of nexus of it's high level and visual enough for all of your stakeholders to be able to understand and meaningfully contribute to, right? I mean, you've got your UI UX designers who are, materially contributing with their Figmas and other things. Your business stakeholders love this stuff. It's very easy to talk about. But it's also specific and well specified enough to actually just derive an implementation.
I actually, I realize I may have set the wrong tone there. I think that event storming is a great precursor into event modeling.
Yep.
Right. So step one is get everybody in the room. Let's understand the problem, understand the data flow. It's a really nice way to do that. And then let's turn that into a measured diagram that we're going to use to go build a system.
That's right.
And identify each data element and how it flows through the system.
That's right. It's a little bit like the distinction between an elevation sketch of a building and the measured floor plan of the building, right? One, a contractor can take real concrete action from. That's the event model. The other inspires, what the end result.
You would never want to, if you were having someone build your house and all you ever saw were the detailed blueprints, you wouldn't really get a feel for what that house is going to look like without those elevation sketches.
That's right.
Right. So you really need to get everyone on the same page. And this is going to prep everyone to understand the events that you have to deal with, the workflows, the users. And then when you come here to event modeling to get this detailed model, it's just going to go very, very quickly.
Absolutely.
Right?
And there's sort of an inverse relationship between the value that this blueprint provides you throughout the software development lifecycle, not just during design, but during implementation, during operations. If that value is high, there's a correspondingly high likelihood that artifact will continue to be maintained and updated and changed when the implementation and the reality of operations on the ground changes. So that's really our goal with oNote, is to really tightly integrate your design artifact, the event model, the thing that you're building the system from, and your implementation process. So once you've sort of done this modeling exercise, what you've got here is not just a picture. You've got a data structure that concretely, in a very measured drawing way, represents the system that you want to build, right? It represents all the work that you need to do. It represents the specific developer tasks that need to be done. And so a feature that we released recently is our first code generation feature. This is just representative. We plan to support many more formats in the future: GraphQL, OpenAPI Swagger, protobufs for gRPC, any number of things. We started with Avro because we were speaking at Kafka Summit, and the Confluent community is sort of committed more or less to Avro as a serialization format. So we generated Avro because that's where we were speaking. But we can generate a lot more formats. We've got good proofs of concept and have played with some of these other formats that we're interested in, especially GraphQL. I think GraphQL schemas are a no-brainer for this, because in GraphQL, you have this really clear distinction between mutations and queries, which is already sort of halfway to CQRS, right? So there's a lot we can do to generate whatever artifact your development team uses in your process from your event model. So now you're, in a very concrete way, deriving major aspects of your implementation from your model artifact. And that's really where a model is vitally important. So if we click this button, Generate Avro, we get this little download here. We can click it. That's where the magic happens. So it creates for us, nobody can see this because it's tiny. Let's extract it to our downloads. So we've extracted this file, pizza delivery, and what this generated for us was two things. First, it generated a handful of event schemas. We organize our event schemas, so that's the order placed schema and the order status change schema that we define in here, and we organize the output of these schemas per event stream. So we have the streams down here, and those represent important causal narratives, and they map to something in your system. We'll see how they map in Event Store. In Kafka and Confluent, it would map to like a topic. So what we've done here is we've output Avro schemas for these events, and these schemas are suitable for if you're emitting these things to a Kafka topic, generally after you put them in Event Store. If you're emitting them to a Kafka topic, you can register this Avro schema with the Confluent Schema Registry, and then your producers and consumers can sync up and know how to serialize and deserialize this particular event. So that's useful from a
peanut butter and chocolate, right?
Yeah, exactly. Peanut butter and chocolate. We like to use Event Store as our primary data store within our application, and we like to use Kafka to move data around the enterprise.
Move everything around. Yeah.
Yep, exactly. So we have our order placed event that shows up on our orders topic. So I would just go to the Confluent Schema Registry and drop this order placed schema on the orders topic, and we'd register it there. Same thing for fulfillment. If we had multiple events per topic, all of the event schemas that we've defined in our model would show up here within the topic folder or within the stream folder. That's not of a special value to us. We'll end up using those things a little bit later on. What's particularly interesting is the other thing we generate with our Avro, which is an Avro Protocol file. Avro Protocol is different from Avro Schema. Avro Schema is just about how do I serialize this to bytes or deserialize it from bytes or to JSON or from JSON or whatever. So Avro Schemas for doing that. Avro Protocol is much more like a protobuf's protocol or interface definition. This is where we're actually defining a set of message exchanges and the schemas that support those message exchanges. So you have schemas inside of a protocol, but the protocol is more about the messages that you exchange. Turns out we've defined those messages, right? We have commands, events, we have commands and read models, and the commands and read models define our web services definition. So by having defined these schemas for the commands and read models, we can actually output this Avro Protocol file. And this Avro Protocol file is really interesting for a lot of reasons. Avro has a native sort of inbuilt IPC format. A lot of people have used that to good success. The 800-pound gorilla in the RPC world right now is gRPC. And you can use Avro Protocol files in gRPC just as easily as protobufs. So protobufs is sort of the default serialization, but gRPC is well designed, and you can swap in whatever sort of serialization format you want. And so we've generated something that we can actually import directly into our implementation. We can generate runtime code from this protocol artifact, and we'll show that to you when we come back. We're going to take a brief recess. This is a long webinar. This is 2 hours of training. Let's take a brief 5-minute recess. We're going to come back at 11:08, and then I'll show you sort of the scaffolding of the application into which we are going to put this sort of skeleton of our implementation in this Avro Protocol file, and I'll show you kind of how we bootstrap an application, a gRPC application in Java from this generated artifact, and then we're going to turn the time over to Chris to talk about how this is all implemented in Event Store. We're going to be writing events to and reading projections from Event Store. We'll talk about how those things work and how that happens. So we'll cover kind of all those implementation bits in the second hour. See you at, let's call it 11:10. We'll come back at 11:10 and resume. Thank you. Welcome back. Yes, we sometimes need a break in the middle of a training like this. So I'm going to very briefly sort of talk about, how do we make use of this artifact that oNote has generated for us, this Avro Protocol. We'll talk about, kind of bootstrapping an application. All of this code that I'm going to show you is in the examples GitHub repo. So please do go clone and play around with that yourself. You don't have to, just watch on screen. You can actually play with it. So I've just posted that again, and I'll make that sticky. So please do go clone that repository, and then you can follow along in your IDE of choice. We are writing Java code. That's mostly incidental. Java does have the best sort of Avro in gRPC support, but other languages are picking up on that pretty quickly, and it's fairly straightforward to wire that yourself. So we could have, done this in C# or in Python. Both gRPC and Event Store have really great cross-language support. So if it's in Rust or Python or some other language of your choice, easy to reach both gRPC and Event Store, with this Avro Protocol file. So I will share my screen again. And this time I'm going to be showing you my IDE. Oh, whoops. Show you my IDE and hide the browser. There we go. So this is just a simple Micronaut application. We just used the Micronaut bootstrap process and generated a Micronaut gRPC application. Micronaut is a commonly used microservices framework in Java. Spring Boot is a sort of close competitor. The idea is, you get a very lightweight sort of dependency injection container for wiring up your configuration and your external dependencies and so forth. So Micronaut's nice. It allows us to sort of schlep off to configuration, some of the stuff that we'll be showing you. The names of streams, the connection URL to your database, all that kind of stuff we can just put in configuration. But the interesting bit here is we've created this class called Pizza Service Delivery. With a little bit of wiring magic in our build configuration, here, this Gradle plugin for Avro, we've dropped, or actually linked, the generated Avro artifacts that I just showed you, in particular this pizza delivery protocol. We've popped here in our source hierarchy. We've actually just created a symlink. So now those files are there for our, in our class path for our compiler to see and our build tools to see. And we've wired up in our build process the ability to see those Avro files and generate Java runtime code from those artifacts. So what this will generate for us, we can actually see here in our build. This is going to generate for us one interface and a whole bunch of classes. So we've got, I don't know what that is, 15 classes and one interface here. And the interface is sort of the interesting entry point. The interface is the primary output of that Avro Protocol file that I showed you. So that Avro Protocol file, just like an Avro schema file, are just JSON. It's just JSON data. The build tooling that I just briefly showed you takes those JSON artifacts and then generates Java runtime code. Corresponding or analogous tooling, it can be found in a lot of different ecosystems. Everyone's got a build tool that compiles protobufs or Avro or whatever to your runtime code. This is especially true in statically typed languages. In languages like Clojure, which is my language of choice, or maybe Python or JavaScript, that is not statically typed, Avro's actually, I think, measurably better than something like protobufs, because you don't need to generate static code. You can just use Avro dynamically and deserialize and serialize things dynamically just with the schemas. So you don't need to generate code like you would from protobufs. But in this case, we did. We're working in Java. It's nice to have generated code, because then our IDE can do its magic. So here we've got this pizza delivery interface that this class that I wrote is implementing. I've got a compiler error because I haven't implemented the proper methods, but I can fix that. I just click the IntelliJ button for implement methods, select the methods I want to implement, boom. So directly from this pizza delivery interface, which our build tooling generated directly from that protocol file that oNote spat out. oNote spits out this Avro protocol. The build tooling then spits out a Java interface. And so this is actually defining all the types necessary to wire this service object into a gRPC service. So this directly wires into gRPC. All the developer needs to do now is just implement these two methods, and the whole model that we showed you at the beginning is implemented from a server-side perspective. So that's magic, right? Like, code completion based on generated artifacts. I mean, this is truly saving all the, boilerplate and bootstrapping stuff that developers spend 80% of their time on. We've now sort of reduced that to now your development team can just focus on, okay, what are the proper semantics for responding to this query, right? We get a query about some orders. How do we properly respond? We got to go look those queries up someplace in an awesome database that we'll show you here in a moment. And then we need to expose the, return those things to the user. And all I have to do to get the web service working via gRPC is just implement this one method. On the other side, the command handler side, in order to accept the order change order status command, all we have to do is implement this second method, this change order status method. Once we've implemented these methods, everything just works. It's pretty great. So the primary task in a query handler is, look up and return data, right? That's all we got to do here. And that's going to be, a read model, or sometimes people call these materialized views. And another word is projection. There's some technical distinctions among those things, but we'll use them interchangeably for now.
Functionally, they're all the same.
Okay. I've seen people split hairs a little over this, but for our purposes, Chris agrees, and he's an expert far more than I am.
2-hour webinar.
Yeah.
We're showing you to go from an idea to a timeline to concrete events to generate your code here. And then I'm going to talk to you about how that shows up directly in your database.
Absolutely.
And every step of that is aligned.
Yes.
It's aligned, it's predictable, it's simple, it's scalable.
Yes.
And it's designed for distributed systems.
And so this is the last thing I'll say before I turn the time over to Chris. The only other task that we need to do to implement this, the main job here is to write an event.
Yep.
Right? We're just going to write an event and trust, in this case, our database code, which we'll show you here in a moment, to process those things into a materialized view for us so that we can respond to the query. So that's it. Code is generated. We've got like 90% of a working application here. In fact, if I hit the play button on this application, it would spin up and start. It wouldn't do anything interesting, but all of the web communication stuff is all wired up. You can call a gRPC client using the same interface file. In fact, using the same generated pizza delivery interface, you can wire up a UI client, which we do. I'll show you a UI that we have implemented in Java FX, and we can communicate between our client and our server very, very easily. So we generated a ton of code, saved ourselves a ton of time. Now I'm going to turn it over to Chris to talk about how all that stuff works in the database.
Okay. So let me share my screen. So I'm going to be pulling out my topic from a presentation I've done a couple of times. Data modeling in an event-driven world. And I am so this is, I'm going to do an abbreviated version of that right now because, we've got a little bit short on time today. If you want to go back and see a more full version of it, we're about to post that up on our YouTube channel, which you've got a link to in the chat right now. So, I'm going to go through this first part very quickly and just talk about our fundamental goals of why we're trying to do this CQRS, why having a database to back your event-driven applications is so important and is critical for event sourcing. And basically, as we build our UI and we add our services, as things communicate, the number of things we have to worry about that can affect each other goes up on the factorial. So this is why one more feature becomes a problem, right? And this is what it creates. This is an actual Redgate diagram of the dependency in a real SQL Server database that does important work in insurance. And that's the policy table there, surrounded by a ring of stored procedures. And we do the same thing when we go into the cloud with our microservices. So how do we get rid of this? This is a little tongue-in-cheek here. I was asked what was the one thing I wanted to tell everyone. And that would be any system with 5 or more interconnected degrees of freedom is incomprehensible. But we can fix that by reducing the permutations. The video that I was talking about isn't posted yet. That's going up later this week to answer that question, Andreas. So we recognize this. This is a classic 3-layer architecture, right? But CQRS allows us to create pipelines. Every component has one channel in, one channel out. Once we've done that magic trick, all of a sudden, now we have pipelines. We can scale the pipelines as long as we have a transactional commit and a guaranteed ordering. Our life, even in the cloud, even in distributed systems, becomes simple. So now I'm going to jump back and talk about types of storage, because I find there's a lot of confusion about what's going on here. Everyone knows relational. It's been the big kid in the block forever. Now we've got additional data models like graph and document databases, which are really great for their targeted areas. But there's an older one that we all sort of forgot about because it was overtaken by relational, and that's ordered. All ordered storage is writing things down in order, right? A log, we all have logs. Ledgers, blockchain, we're all very familiar with ledgers and event streams. And so now what we're talking about is, what does it mean to have a database with the transactional guarantees of a database for your event streams? The application storage patterns also have a lot of confusion around them. So I want to quickly define those, because a lot of pain and trouble comes from misapplying the various things here. One of the things I love about oNote and the event modeling pattern is it makes it super clear. This is a Turing machine. When I do this live, I ask the audience, but I can't really do that here. This is a physical implementation of a logical Turing machine, which is the heart of every microservice you're ever going to write, everything really that we write in computer science. And what you see is that you have an input, you have some state that's read from that tape at the bottom, and an output. The only difference we're going to make here is we're going to have it a one-way, I think that's a transducer, a one-way Turing machine. We're only going to append, we're not going to go back and rewrite anything. If you're saving the inputs, you're command sourcing. If you're saving the internal state, you're either change logging, change data capture, or you're state logging the whole state. If you're talking about like a warehouse, input would be add a box to the warehouse. Change logging would be inventory increased by 1. State logging would be we have 80 items in the warehouse. But the last one, which is event sourcing, is we save the output, and that would be something like box added to warehouse, right? And that's what we put in the history log, and we want that to match the business model or the domain. We want a series of understandable events from the business domain in the log. That's because the challenge with the other two methods of command sourcing and state logging is you need that service to understand what they meant. And if you don't have that service, you've got to translate them. And version 1 and version 2 of the same service are effectively different services. And this is where we get in trouble. Once we've made this an external model, now we can say it's in the business terms. I can write a new service. I can do things. I can version things. Life becomes simple again. So event sourcing, properly defined, is application decisions are persisted as an immutable sequence of business events, not database, not inventory level changed or, +1 or -1. So a stream database, event store, says we have a core event log that records everything, and then we're going to have fine-grained streams inside that log. And you'll notice here that each stream has an incremental ordering of its own, and then there's a global ordering of all of the events. And we allow you to create projections or the materialized views that Bobby was talking about, which can reorder to give us an atomic sequencing on some subset of those events based any way we want to do it. And this is, if you're familiar with Kafka topics, you could think of those as a table. These are more like a row. So you would have millions and millions of streams in a stream database, each with an incremental stream ID. So the way these applications work is we have our services, they're going to read from a particular stream, and they're constrained to write to the one stream that is their source. But then event processors or readers or read models, they can read from the entire database safely because we've got the transactional guarantees on what gets committed. So what you're looking for is fine-grained streams, sequential numbering, global ordering, optimistic concurrency. Now let's take a look at stream categories. And that's where we take a set of streams in an event store. We just use a simple hyphen notation. You'll see this later to say for this category, we have an instance. So if you have invoices, each stream would be an instance of an invoice with all the events on it. The category would be invoices. So we provide ordering at both levels as we do that. And then we provide a global ordering across everything, say customers and invoices, so you know where the whole system is at any point that you stop. So let's now talk about the data modeling. So we just created a couple of events. We've got them in there, but we know as we build bigger systems, we've really got to be able to model this data and have it be understood. So I'm going to talk about how we rederive formal data modeling in events from the historical perspective. Cod was the person who first created the relational model. And what he said was a relation is a schema on a tuple, which is this row here. And then when you group those together, you get a table. So a table is a group of tuples with the same schema. In event sourcing, what we're going to say is that the tuple is the event. So we're going to not just have these as anonymous objects, we're going to name them. And that's going to be very important. So if we go back to what I was talking about before about customers in invoices in a classic third normal form diagram, I can see here that I have customers with an ID, invoices with an ID, and then related tables. When I find the categories in this model, I say, okay, customers is one category, invoices is another category. And what we see then is that the customer, I've got customer 1 and customer 2. That maps here to this ID 1 and ID 2. And when I look at this, I can see I've got an event stream with a name and then an update that goes into that schema. So this is going to show up physically right in the database. Bobby's going to be able to show you that in a minute. So I can see here that add customer 1. If I look here, I see that the payment terms on customer 1 are net 90. Payment terms on customer 2 are net 30. When I look at an event source system, I get a story. I can see that I add to the customer and then they negotiated a term extension. But customer 2 was set up and they've not had any changes. When I look at the invoices, now I'm going to see some more items here. I've got subtables for line items and for payment status. And I can see the IDs match. So client ID here. And I can see that line items I got 1, 2, and 3 are about table 1, and number 2 is about invoice number 2. Here I can see invoice number 1 was pretty straightforward. We created the invoice, we added 3 line items, and we got paid. Invoice number 2, we added the invoice, we added a line item, we removed a line item that's now missing from that data, right? So we added 2 and then we removed 1. So that is how you can think about moving from the data modeling and bringing the data architects in to say how we're going to have a cohesive understanding of what the events are and use all those tools that we've learned about good data modeling in the system.
And we saw, sorry, Chris, we saw a little bit of that in oNote when we're designing our schemas. That's where you'd want to engage these professionals who have been doing this for a very long time, these data modelers. It's important to engage them when we're building out those schemas, because those schemas reify in exactly this way that Chris is describing in our implementation.
And for the internal system, so I'm going to call the Event Store database your private database, right? For that schema in the Event Store or any database you're writing to with your app, you want that schema to be private. You don't want other apps to see those internal events, and you want them to have a third normal form sensibility. They should be sparse, they should be change only, and they should be private to your app. Because if you publish them everywhere, you're going to get locked in, you're going to get distributed monolith. You're not going to be able to make changes, move things around, update things, because everyone's consuming them, and you make a change and it doesn't work. Bobby's going to show you a very easy way to use the projections to create those public events you're going to want to then put on Kafka or other systems and publish to the world. Another way to think about the category is that it creates a data union or a sparse column. So the assumption is that any field on an event inside of a category, because a category is going to have a set number of event types, the fields in them that have the same name mean the same thing. That allows you to create a union of all the different types and assume that any update is a change in that value, which gives you a very simple fold to say, here's the current state of this item in this category. So the other thing that Event Store provides is what I'm referring to as quantum consistency. Full name is distributed consistency via atomic prefix incrementation, which is why we went for the short name. It says very simply that events are the minimum information packet, or quanta, which is where quantum comes from, not from the uncertainty side, but from the quantumization. New events are linearized, sequentially numbered, and we have a transactional commit on those events. And then any consumer of that stream, because it's atomic, it's 1, 2, 3, 4. You know, if I've seen event number 3042, I've seen every event before. And if I haven't, I can go back and read it and restore myself. And we provide that ordering not just the top level, but also down to the fine-grained streams. So a service can go restart just this particular invoice and not reread everything, right? So again, talking about how the writers write into a particular stream, readers read from everything. So let's look at this. So when we talk about writing into Event Store, we write the events 1, 2, 3, 4 all the way forward because we're writing our log. But consumers are going to see those in reverse order. You know, event 1 is going to distribute through our system. You can't get away from the physics. When you're doing something that's truly distributed, that propagation is going to occur. But, you know, a lot of people sort of talk, well, that means you got eventual consistency. No, eventual consistency is where you just throw up your hands. This gives you atomic ordering. So I know that my analytics system is at position 2. I know my external integration has seen event number 3. I know my memcache, my UI are exactly in sync with each other. These events are going to be moving very, very quickly. They're going to distribute, and I can set SLAs for how long I'm willing to allow them or how stale I can let them be. The other really important thing about this is if I've got something that's listening on this stream and taking action, because I've got a database, because I've got those transactional guarantees, if I have a process manager that's at position 8 and it tries to write an update, it's going to get rejected, right? Because it hasn't seen current states. I've got another service that's looking at the UI display. I have a user command. The user may be only position 6, but the service knows that we're at position 10. So we can accept that command, make a change, and place it in, and that will become the new event 11, right? So this allows us to have pools of distributed consumers that don't need to coordinate. I don't need to worry about, well, what if this event gets processed here while something's happening there? The database linearizes and gives us transactional updates, and our consumers now have comparable positions. And that's tremendously important. I can predict what's happening. I know how far they might be behind. They're never wrong. They're only stale. And all of this is the benefits of atomic ordering and immutability. So for paying the small price of not being able to go and log into production and edit a field, we get a much saner, simpler model in distributed systems. So, and this is how that works. So we have that, the event log, then we have multiple streams, each with their own, and then the categories are in effect projections of those low-level streams. And then how that works in a larger system is you're going to have the writer and the event store and the processor. These hexagons represent your application boundary. So this is your private schema if you are running in an enterprise system, right? This is your schema definition in the relational database, or this is your event store. So all the related services that need ordering between them go into one event store instance. And those produce that internal state that app uses. And then we use a projection or some other mechanism to produce a public document or event that we then push out onto our distributed event bus for downstream consumers. And those internal events, again, are going to be third normal form. That's going to give us, in effect, a smaller footprint than a traditional database. Because everyone always has, I'm going to jump back here, their ERD diagram up there about this is what's in our database, this is what we store. But they don't list their audit schema and their history schema and their reporting schemas. They skip those. So what I find is when you actually have the source data and you do it in a third normal form inside an event store, you only keep what you need. And all of those public schemas, that reporting schema just gets distributed to the public bus. It can be regenerated at will. If something outside falls down, you call back to your source. You say, hey, here's where I was. Here's where I need to be. Can you restore me with these events? I need this range of events from here to here. Replay to me on a direct channel. Don't re-spam the universe by replaying everything onto a bus. Now we don't have to make everybody idempotent in really complicated ways. They just keep the position that they know about. Anything event they see before the position, they throw away. If they see a gap, they know to call back and say, hey, I missed something. Restore current state. Everything gets really simple because of this transactional and deterministic processing.
Yeah, and we'll see an example, Chris, of you mentioned sort of writing internal state out to the public event bus. The inverse is true as well. We can observe events that some other application is generating, which we see in our model here. This order placed event, we didn't make that. Some other upstream system made that. We perceive that on the distributed public event bus.
Yep.
We don't just see it go by. We actually copy it to our local story, our local internal narrative, so that we make sure that that has a place in our causal history.
I should add an arrow here to cover that.
Yeah.
So it's incredibly important. So these apps can be listening to the public bus, say, oh, I need to react to that, write down an internal notation that they're reacting to this particular thing, and then they can produce new events out or new behaviors. And by breaking it down, we really break that complexity. Because again, every one of these things now gets this benefit of this one-way pipeline. I'm consuming this, I'm making my decision, I'm putting it out. And the key here is you commit when you're done, you write to a transactional store, and then you can share the event with whoever you want. I've seen lots of things worried about, well, the double commit problem, this, that, the other thing. That's people who are publishing their internal state directly to a distributed bus and doing storage or updates after the fact. If you run everything through a store that gives you that distributed consistency, then all these problems just go away. And by using an atomic increment, you know where you're at. Idempotency is easy. Cache invalidation is easy because you're not. The only way you invalidate a cache is to move the cache forward. Your systems are never wrong. Everyone, you think about eventual consistency, Facebook with updates does it all the time. It's the scale is brilliant, but it's really kind of annoying to see updates disappear and show up, and I get a notification once or a notification twice because it doesn't know if I've seen it. Because they're doing basically everything will eventually someday in a week, it's all going to be stable, right? This is entirely different. I've got determinism all the way through and a simple pipeline. And then once I've got those pipelines, I can scale them out horizontally, and I can push all those idempotency current state checks to the database, just like you do in a traditional application. That's really why we like the database in a standard on-premise app. I don't have to worry about managing 5 files. I just go, well, I'm going to update the database. Everyone's going to see the database at one position. The one change we have to deal with, because we're distributed, is that we include the time. Over time, so now it's not, I don't have one now like I do in traditional database. I've got positions. Everyone at position 20 is the same. Everyone at position 5032 is the same. And I know how to go from one to the other. And I can compare them so I know how far off I am.
Yep.
So now I'm going to hand it back to Bobby so he can finish up.
Absolutely. Chris, thank you so much. A great explanation of the value of Event Store. And sort of the takeaway message for me is that if you're designing event-based applications, you need to be using Event Store. And you need to be using oNote in conjunction with Event Store, because the event modeling process, the artifacts we generate, go hand in glove with Event Store. We'll show you an example of how that works right now. I'll share my screen.
Yeah, I would say if you're not going to use Event Store, I would use something like SQL's or Oracle, and you're going to have a lot of pain with the mismatch. But don't use change data capture, but you need that transactional commits.
Yes.
Right? Yep. And you really want something that's aligned.
Yes.
And that's Event Store.
Yep. So what we did here is I'm actually showing you Event Store. This is an instance of Event StoreDB just running in a container on my machine. What's really cool is I'm running it ephemerally, so I can actually sort of rebuild all this state at will, which is super cool. And what we did, going back to our implementation here, we need a way to read the orders, okay? So let's look at our model. In our model, we've got, we see this order placed event. It shows up somehow. We're not really sure how that shows up, but we need to capture that and store that locally so that it's a part of our history. In terms of implementation, we need to store a local copy of the event placed event. If we see it go by on some public message bus or whatever, we need to store that locally in our totally ordered state, like Chris described. And then we need to incorporate that event into this orders to fulfill. So every time an order is placed, we basically need to add an order to this to-do list of orders that we need to fulfill. How do we go about doing that? So what we did, and this code is checked into Git, it's under projections within the Event Store implementation. But the way we did that is we built projections. So we created this orders to fulfillment projection. Event Store is super cool because I can just write these things in JavaScript. And then whenever anything gets written that I'm interested in, I can listen. It does all the stream processing right within within the database, and I can emit new events. So what I did here is I said, I'm going to watch this orders category. I'm going to pretend that I don't own this orders category. I'm just going to watch it every time any order, any order on any order stream is placed. I'm going to take this and I'm going to emit a whole new event onto this fulfillment stream. So I'm going to create a new fulfillment stream just for this particular order, for the fulfillment of this particular order, this order ID. And that's where, in this fulfillment stream, that's where I'm going to track the history of how this particular order got fulfilled. Really neat thing about Event Store is that streams are short-lived and specific to my particular entity that I care about, right? In this case, it's an order. I want to track the whole history of the order. I don't have to recreate that from a totally ordered thing with a bajillion other orders. I just want to see that particular order, and I can because it's on its own stream. It's also, as Chris pointed out, in a total atomic ordering, but within this stream, I can just see the events that I care about. So as anything happens in this orders category, so that could be order -1234, that can be order -4321. When any order placed event shows up in this orders category, I emit an event to the fulfillment stream. Okay, so now I don't have to, I might not have write permission to the orders stream because I'm not responsible for orders. Some upstream team is responsible for orders. I am allowed to write to fulfillment streams. So I'm just going to write, I'm going to observe, and maybe it's a public message bus. Maybe this order is happening on Kafka, and I perceive that. I write it down to my fulfillment stream. So that's one projection. That's sort of the less interesting of the two, perhaps. But this JavaScript code is in the repository. The fulfillment status read model now, in turn, watches the fulfillment category. So the thing that I just wrote to by observing the orders category, now I'm writing to fulfillment related stream. So anytime a fulfillment related event gets written, I'm going to do this little transducer, right? And I love this because there's a very clear, I'm a functional programmer, so I really like, function signatures. I want to have really clear function signatures about what I'm doing. And this really is just a fold or a reduce over an infinite sequence of events. So we write what's called a transducer. That's just a reducing function with the context of how things arrive at the front door and how results go out the back door. So that's a transducer. And this function is a very simple transducer in JavaScript, right? When, at the beginning of a particular fulfillment's history, or at the very beginning of this projection state, I'm just going to initialize an empty projection, right? This looks painfully familiar. This is the schema for the read model that I defined in oNote. I said, hey, this is just a map with an orders key, right? And this orders key is going to store our orders. In this case, we're actually indexing it on ID into a map instead of just having it in a flat sequence. But the result is the same here. So every time an order is placed, remember I copy that order placed to my fulfillment world. Every time I perceive that, I'm going to go ahead and add that order to this collection of orders under consideration. This is the set of orders that are in my world as a fulfillment person. These are the things that I'm working on right now. So I'm going to add that when an order is placed. And then when the order status changes as a result of me working on my fulfillment app, it's a little more complex, but it's very straightforward, right? In the case that the new status is that the order was delivered, I'm actually just going to remove this order from the collection, right? We're done. It's delivered. Once it's on the customer's doorstep, we can't take it back to the store and put it in the oven, right? Once we get to deliver it, it's delivered. So once we deliver it, we're just going to remove it out of this read model.
So that's going to give you an event that's going to list all of the current orders.
That's right.
And every time you get a new event in, a new event with all of the current orders,
that's right.
It's written, and that's perfect for pushing out to another system.
That's right.
Right? Because when you're doing those public events, you don't want that system to have to call back. You want it to have everything it needs right there.
That's right.
In one broad event.
Yep. So if anyone downstream is interested, this is exactly, to Chris's point, this is exactly the kind of stream that I could, pull from being internal and push it out to a public place like Kafka. And now this represents the history of my state, right? This is at any point in time, this is what our world looked like. We had 5 orders in process or whatever. And you start to do the kind of analytics in that public message place, just derived from our internal state.
And because you've got the public state on there, you don't need the history. Anybody can wake up and get the most recent one of these.
That's right.
And they know where the system's at.
Yep.
Because they're not internal to the app.
That's right.
This block state is perfect for these external applications.
Yep, absolutely. So in the case that the new status that arrives in this event is something other than delivered, right? I'm putting it in the oven, or I'm starting to prepare it, or it's en route, I put it in the car. In that case, I'm just going to update the order status of the order having this ID. So, right? So I've got the order ID. It shows up with the event. I've also got the order status that shows up with the event. And so I'm just going to find, look up the order with this ID, and I'm going to change its status to the new status. Easy peasy. So now my new event contains all the orders that I'm dealing with as just a JSON object, a JavaScript object. Super easy. So I didn't have to write any of that code in my Java application, right? All that code is done, using Event Store's built-in stuff. And what's really neat is I've got a process at the closure REPL here where I'm just producing new order events onto the topic. So I'm this is pretending to be some upstream system that's producing these orders. As I add these orders into the world, this actually updates, and now we've got a whole bunch of additional orders that have been newly placed. Here in my UI, this is just a JavaFX simple UI written in Clojure, and it's using the gRPC interface definition, that Java interface that we derived from our protobufs or our Avro file. And I refresh it, and we've got new orders placed in here, right? So this thing is connected not to the database, but to our service that we were working on defining. Let's go back to that service real quick. So I've pasted back in the implementation of this thing. Here, in orders to fulfill, we are simply going to the projection client on the database, and we're saying, hey, get me the result of this fulfillments projection, the one that we just showed you here. Show me the fulfillment status projection, and it does. And then I just pour the results of that into my response type, and then I return the response. So when I hit this refresh button, that's what I'm getting. I'm getting, a new query of, hey, what's the latest state of this read model in the database? Easy. When I go to change the state, so if I, click this one as Mark is preparing, I click it, and then it updates because it clicks and then gets the latest state from the database. So now it's no longer placed. I can put it back in the placed state, but I usually want to, move it forward. Now it's in the oven, and now it's en route. And now when I deliver it, it disappears, right? So just the way that we'd expect, without having to write any of that code in my Java service, all that's happening on the database. So Event Store is extremely powerful for writing the links in our model that go from event to read model. Event Store really shines. This arrow right here, right? This arrow from order placed into orders to fulfill, and from order status changed into orders to fulfill. Both of those were implemented using JavaScript and Event Store. Didn't have to write any Java code for that.
And no server to run, no service to do it.
No.
And when you commit to Event Store, that happens, and it gets emitted and dynamically pushed to wherever you want it to go.
That's right. And it's very easy to scale. Event Store, they have a cloud offering, Event Store Cloud. I recommend you check it out. And it scales, horizontally as big as you need it to. So as your workload grows, it's very easy for Event Store to grow with you. And all that awesomeness about state and total ordering and causality, all of that stuff grows with you as you scale.
So we do have a question about if I can use PubSub using Event Store, why would I use Kafka/Event Hubs to communicate across microservices? And that's really a matter of scale. So if you have a set of microservices that all work to do one aspect or one job, you probably want them all to talk via PubSub on Event Store. But once we get to other systems that we don't know about, future systems,
other departments,
systems,
Yep.
That's where that distributed event bus really shines. So all the things that work together to run this aspect of your business, hook them all up directly. They're going to get things pushed very nicely.
Yep. So great answer, Chris. I think that's a common thing. And people talk about, oh, well, Kafka or Event Store. No. Chocolate and peanut butter. Chris always says chocolate and peanut butter. They're better together, right? Internal state is Event Store. External or public state is Kafka.
Yep.
So
we got about 4 minutes left, Bobby.
Yes, thank you. So this arrow from orders to fulfill to the interface, that's where we implement our our query handler. So our query handler, that particular arrow is our responsibility. We write it here in Java. We look up the state of the projection in the database, and we respond with it. So that's that arrow. The causal arrow here, where we're going, from interface to command, and from command to event. Really, the arrow from command to event. This send here is actually done in the client where we send the command. But the arrow here from command to event, that's our command handler. So that's our change order status handler. So here we get this request in, we build an event, the order status changed event. This is actually one of our generated classes, our data transfer objects that was generated for us by our Avro stuff. We actually added a little bit of art here, Chris, where we can build event store events from Avro data.
Yep.
So we build the event store event, and then we simply append that event to a particular stream. Obviously, we're going to keep the name of this stream the same. It's just going to be fulfillment dash whatever the order ID is. We're going to append to that stream this new event. And when we do, all the magic happens in the background to do, this arrow from event to read model, so that our read models are all, and our projections all automatically update in the background. So really the only code that I've written here is sort of, this arrow to respond to a query, and this arrow to handle a command that I've received and publish an event. Those are the only two bits that I've written. Yeah, that's the business logic. That's the valuable stuff that makes my service unique. And that's what I implement, in my programming language of choice and deploy as my artifact. So this service has been running the whole time. As I said, this UI over here is just a ClojureFX UI using the same generated interface to bootstrap a gRPC client. And, I can mess with all this stuff as much as I want, and everything just works. So we're preparing. Now we're in the oven. Preparing, in oven, en route, delivered. Now it's gone, right?
Yep.
So we went from idea to design, making our idea more concrete in an event model, to data models within that event model to track exactly how our data is moving, to generated Avro artifact, to generated Java runtime code, to a running service in the course of 2 hours?
And that service is fully ready to distribute and scale.
Yep.
And have multiple workers, and they're not going to conflict. And you can add a new service to that you never thought of before, and it's going to work just as well.
That's right.
As something that was there on day one.
That's right. So that new use case, if in true sort of DevOps agile fashion, we get this first version of the app and we deploy it, and now it's adding us business value. If we come back and the managers are like, boy, I'd really love to monitor, the drawdown on our inventory that's represented by these order fulfillments, that's easy. We didn't have to plan for that. We didn't have to know what was coming. Just because we've designed things the right way and implemented it the right way, we can very easily take on that next use case with very clear contracts and just build it.
You put that process manager in and say, okay, once I see 50 pizzas sold, place a dough order, place a this order, do these different things.
Yep.
Having never seen anything else.
Exactly. So this is a very powerful way of designing and developing systems. Event Store and oNote work hand in hand, work great together. Event modeling, I want to give thanks to Adam, who I believe is on this webinar.
It's great stuff.
Great contribution, Adam. We really appreciate event modeling. So please do sign up for oNote, sign up for Event Store Cloud, clone the repo that we sent out, and go to town. Knock yourselves out. You can actually bootstrap the very same app in your own Event Store Cloud, and you can play around with the UIs a little bit. It was a pleasure having you join us. The webinar is ending now, but we will stay on for another 5 minutes or so if you're interested, and we can take a few questions.
There's a link for Event Store Cloud. It's self-service managed hosting.
Yeah, it's great. I was playing around with that and with the Docker version in the course of implementing this. It was a joy to use. It was very easy to get started.
Yep.
Any questions from the audience?
It seems like Jimmy Ferris says he has the motivation for learning oNote now.
Oh, good. We're pleased to have you as a user. That'd be great. And we will be releasing additional intermediate representations like GraphQL and other features in the future. We've got a lot of good features coming down the pike.
Okay, so Bobby and I often mention that each event is independent from every other event from an ES standpoint.
Oh,
and
it
that
disappeared.
went away. So could it clobber current state? So yeah, so there are times where so the way you want to design your events, and one of the reasons we like Java JSON, right, is because it gives you the same benefit of a table in a traditional relational database where you can add new columns as long as you give them a default. And that will let you expand what's going on, and you can do that in the category. So if you have a new concept that comes in, then you can either add a new event or you can expand a new event that you've already got, right? But if you do have a change that's really going to completely upend what you've got going on, almost always that's a new thing. Is you just create a new category or a new set of streams and you cut over. So there's a really great book on that's really a versioning problem. And Greg has a really great book on LeanPub. Let me see if I can put that up there.
Yeah, so I think part of the question, so that question flew over into the published tab.
Is that where it went?
I think part of the question there's about versioning, but I think that there's a simpler question. I think it's just about some new event comes in and it clobbers the previous folded projected state. Yes, absolutely. So projections are mutable in some respect, right? We can change it. They're not really mutable because they're recorded immutably at each change. But you can delete keys just like we saw in our projection. They're absolutely mutable and changeable.
So internally in your private schema, so I misunderstood the question. My bad. So in your private schema, you're always appending things to the streams. But as you publish things publicly, very often you want that full replacement. The most current version of whatever is the total current state, you want it to replace it. So you want to have that whole, here's current, you can forget everything else. Because you don't want an external consumer having to read your entire history to get someplace. Internally, you want to use that, right? When you're dealing with what your app does and how I reload this invoice. But if I want like payment status for the month of November, I just want payment status for the month of November. And if I update it, just drop the old one and replace it, right? We don't need to keep that. So you pick which one you want to use. Can't hear you. You're on mute, Bobby.
I was saying all kinds of interesting stuff. That's another great feature of Event Store is having short-lived streams, so that if there is a bug in your code that is breaking projections in some bad way, you can upgrade that projection code, and it's only sort of the set of streams that are in process that are going to be broken, right? So you can sort of move on beyond those things, and a lot of times there are code changes you can do that will accommodate and handle in process things, and then make new things in a better way, and then you can sort of migrate to the final version of that projection code. But yeah, the code that creates the projections, just like Chris said, it's a pipeline. It's downstream. So the events are the source. The projections are derived from the events and actually represent events themselves. But the projections are derived from events. So if you don't like the projections, just throw them away and rebuild them from. I did that several times while I was working on this. I didn't, amazingly, I didn't write perfect code the first time, and I was still learning the projection API. in JavaScript. So I just threw away and rebuilt the projection several times, and those source order events are still there, and then I derive them into fulfillment events, and then I derive them into the current state of the orders to be fulfilled. So it's easy.
A huge concept that's really helpful is to really just drill down on source of truth and derived data. And that derived data could be a user screen, it could be a projection event, it could be a whole reporting database. You could be feeding all your events into Snowflake or into a SQL reporting system or into anything. It's all derived. It's all recoverable.
Yep.
It's all checkpointable. So you can do intermediate caching and restore it very quickly. But all of it needs to be able to be rebuilt on demand. In practice, you want faster recovery methods, and that's why we're going to do intermediate snapshots and caches. But as long as you say, okay, this is all rebuildable, this is source of truth, then everything simplifies.
Yep. We have another question really quick, and then we'll come to a close here. Jimmy Frills asks, do we have any getting started templates with the JavaScript implementation all the way? So yes, the repository that I link here, I should have made that the answer to your question. Apologies. The repository link that we sent out earlier, Jimmy, has this full example. All the code that we showed here, including the JavaScript projection code, is all in what did we call that? Java.micronaut.event or Java-micronaut-event store, that directory. There's a projection subdirectory that's got the JavaScript in it. So you could spin up your own Event StoreDB and be off to the races, just doing what we did here. While we're still working on those templates, though, as a disclaimer, Jimmy, no doubt we'll find things that are confusing or need to improve the READMEs or whatever. So we're working on those templates. But yeah, it's our we've published them; they're public. It's our intention to maintain a really great set of examples that are well documented, easy to get started with, that incorporate oNote and oNote models and oNote generated artifacts with these other technologies like Event Store, gRPC, etc. Oh, another language, JavaScript backend. No, we could easily do that, though. Chris has offered to contribute a C# backend. JavaScript would be fairly straightforward, Node.js or whatever. Be really straightforward to do that. Yep. So that's not in there yet. Right now, it's Java enclosure because that's who I am. But we've got pull requests accepted, and we will be working on other languages as well.
Yep.
Great. Thank you all so much for attending. Thank you for your time. I hope you learned something valuable. It was a pleasure to have Chris Condron on with us. Thank you, Chris, for joining us.
Pleasure to be here.
And we will see you again next time. Thank you.